Tomar sir, we can start.
Very good afternoon, dear students. Today we start the sixth lecture of this module A, and today's topic will be performing the experiments. I again show you the chronology of the steps of a research process and where the sixth aspect is collecting the data, or essentially which is the heart of the execution of the project. So today we will discuss what are the points that you need to take care while performing the experiments. Okay. So certain aspects are very important while performing the experiments in the laboratory or in the field. And these are all, though they are of common knowledge, but they have a lot of importance when it comes to the final results. Your honesty is reflected in the final result that you will be showing to the world out of your work. And also the patience with which you have to work. Many a times there are failures and one may get frustrated. In fact, research is at times is quite frustrating. So that is not to demotivate the young people from taking up research as a career, but it does require a lot of patience, particularly when you find results are not coming the way you expected, but don't have to lose the heart. So you require tremendous stamina, perseverance. You might require to be awake for 24 hours sometimes. So, and you also work with the precision and the devotion to the subject. So all these are the qualities of a good research worker. And in addition to that, you need to have the imaginative power. So don't have to just follow the routine of your experimental procedure. There could be a lot of surprises, and we should be able to look for those surprises and seize the opportunity to look for something new. So you don't think that everything is known in my subject, so there's nothing new to add. So there could be surprises, and one should be able to catch those surprises. And you require an analytical mind to catch those surprises. So need to have imaginative power to think about the different aspects of your research work. And very important is that each and every bit of the task that is a part of your research work has to be done by the researcher. So many a times, you may have a group of co-workers, but if it is a part of your PhD, it's good that you should do it all by yourself. Do not do the entire work in collaboration with others, because at times your work may involve like characterization by different techniques. You make a sample, give it to different laboratories for analysis, and then they themselves do the interpretation and you write the paper. You will not get the feeling of that work. So in fact, it's a very good idea to go to that instrument, even if it is not in your laboratory, see how they are collecting the data, how they are interpreting the results, so that you know every aspect of the work that is a part of your thesis. These days, particularly when your work is a multi-laboratory work or multi-techniques work, then you tend to don't give that much of attention on other techniques other than what you have in your laboratory. So, but it is very important that if it is a part of your thesis, then you must know each and every aspect of why did you choose that technique. You should be very much convinced. And the conclusions depend heavily on the quality of the data. And therefore, you have to be doubly sure about the correctness of the data. That is why when you are giving samples to other laboratories, then it's better that you are present at that time, because there could be some untoward incidents, some surprises, some events may take place that may distort the data. Therefore, it's good that you present yourself at that time, so you know the complete history of the experimentation. Now, so there is a proper way of carrying out the experiment, not only experimental work, but there are many aspects related to carrying out that experimentation. So these are the points I have mentioned. There may be many more, and I will explain to them all these aspects one by one. So the importance of recording observations. So you should record whatever observations you are making. You keep a record or record those observations, whatever you are having. So you maintain a logbook, write in your logbook what you are observing. So maintain the records for verification of observations in future, because you may get some surprises and you write them, jot them down. Later on, when you are trying to analyze your data, you can come back and see what happened at that point of time. Similarly, the history of the samples may undergo changes during transportation. So you have to have complete history of sample, at what point of time, from what place you collected the sample, and then till you analyze those samples, what are the steps that samples have undergone. Then the data recording has to be very transparent, because it is the data which speak for themselves. So whatever data you are acquiring, this should not be tampered with, or this should not be, like many times we have a habit of smoothing the data. So smoothing should not be ventured in. Use the data, at least you should have a record of the raw data, because that is very, very important. Then the quality assurance. Quality assurance means whatever data you are generating, what is the quality of that data? That depends upon the instruments, the methodology that you are adopting. So you should check the performance of the instrument with standards. So whatever data you get out of the instrument, how much you are sure that the data is correct. So for that, you have to have a quality assurance program. Your instrument must be giving the proper results. For that, they should be well calibrated from time to time. Then the error analysis is very important. There could be errors of random in nature or systematic errors, so you have to minimize them. And there are means and ways to minimize those errors. We will discuss in more details. And in addition to that, there could be unknown uncertainties. See, particularly when you are studying a new phenomena, new aspect, you might not have factored certain aspects, might not have thought of that it can happen. So those things which you did not envisage in your project, in your program, can also affect your work output. So be ready for some surprises or unknown uncertainties. Okay. So one by one, I will discuss them in little more detail. So it is very important to record your observations in your logbook. When you are analyzing the data, there could be some surprises. So for example, if you are handling an instrument, then if there is a glitch or a voltage fluctuation or a power failure, that could affect your results. One of the examples is like, in the early 90s, when there are laboratories working on cold fusion, they are studying the electrolysis of NaOD in a beaker and measuring if there are any neutrons, because when the fusion takes place, DD fusion takes place, there will be neutrons generated. So the neutron detectors now, they are very susceptible to any fluctuations. And people who have been maintaining the logbooks, whenever there is a burst of neutrons, they really get elated. They start noting down the counts, neutron counts. Suddenly there is a big jump in the neutron counts, and many people almost came to the conclusion that they have seen the cold fusion happening. So, but then The most important part is that it should be repeatable. That is where this kind of experiments could not be repeated because it happened only once in a while. So if something happens once in a while, it could be due to these fluctuations that can happen sometime. Then if you are working in a particularly in a machine which needs to be operated for a long period of time, like 24 hours or no, 4 days together, like accelerators or big machines, then there will be change of shift, change of operator. And at that time, different operators have their personal habits or biases, So if they have to do some setting of the machine, there could be some changes in the situations. So the results might get influenced by how the operator is handling the machine. So change of operator. So if you are noting down, recording your observations, and at particular time something happens, later on you can check and see at this point of time what happened. So it could be change of operator, it could be a voltage effect, particularly sometimes, when the offices close at 4:30 or 6 o'clock, the electrical load comes down. And at that point of time, there are some fluctuations. Similarly, in the morning, when all office instruments start getting on, there are some fluctuations. So all those things are important to note down. Then there could be minor incidents in the laboratory, could be some spillage, some leakage, or you get a visitor, and that may lead to some distraction. If you are noting down some readings and suddenly you have got a visitor or there's something happened, and you might have made a mistake in reading down the reading. So that later on, when you will analyze your data, you may find one point is not fitting into your scheme, and you try to recollect what happened at that point of time. So the time profile of your data is very important. Like, in accelerators or big machines, there is an automatic logging. So this keeps on recording what happened at this point of time. The machine automatically records. There could be change in the temperature due to fault in AC, and the temperature dependent changes may take place in the instruments. And if we are going to have a survey of human beings, of some sample surveys, then human subjects, So if you are interviewing people and some people are very smart, they may not give you proper information. So there could be bias in the people whom you are surveying. So all those things may lead to observations which may not be the correct observations. So maintaining records is very important. Always maintain a logbook, though it can be a soft form also, to record raw data and observations. So whatever data you are generating or your instrument is showing, keep noting down. Any fluctuation in the extraneous variables should be recorded, like voltage fluctuation, glitches, temperature, humidity, etc. So keep a note of those fluctuations. Change of operator of an instrument, it could be systematic, it can lead to systematic errors, and the key observation of parameters. So whatever parameters are to be taken note of, if you observe them, whether they are proper or not. I'll give you an example of a Pelletron experiment in TIFR, which I was myself witness to. So in Pelletron experiment, we were doing an experiment on heavy ion reactions. Like we have a projectile beam of carbon and bombarding a thulium metal foil. And we told the operator that we need 72 MeV beam energy of carbon. Now, for the information, that beam energy of carbon or any projectile is calculated by the charge state that we take Q plus 1 into the voltage, terminal voltage in million volts. So from the carbon, we can have 4, 5, 6 plus charge states. So whatever the charge state you take, plus 1, because we start with the negative ion. So Q is the charge state, V is the terminal voltage, and you can calculate. So if you want 72 MeV, we need terminal voltage 12 million volts. Take 5 plus charge state, that will give you 72 MeV. Now in the control room, there is a magnet, that reads, there is a reading, and that will tell you this is the terminal voltage. So that terminal voltage should be 12. So it was 12.000 or something like that. So based on this, if you are getting some beam, then you expect it to be 72 MeV. So everything is going very fine. But then after the first experiment, I took the sample to the laboratory and I took a gamma spectrum. When I take a gamma spectrum from the 72 MeV projectile carbon 12, I expect that the products, some products, their gamma spectrum, I know what gamma lines I should see. But I found those gamma lines are missing. And whatever gamma lines are shown in the gamma spectrum, from there I guess that it is not 72 MeV, but it is 50 MeV carbon B. So doubting the accelerator people that they are not giving 70 MeV but 50 MeV is a big, you have to really be 100% sure before you tell to the operator that this machine is not running at 70 MeV. So anyway, I was so much convinced with the gamma spectra, I went back to the operator in the night, it is about 12 midnight. And I told the operator, your machine is not running at 12 million volt, though it is showing 12 million volt. Then he asked me how I am sure. I said, I am 100% sure because my spectrum is not giving me products which I am expecting. So he called the peloton in charge who was living in the colony, TIFR colony. He came and he was again came to me asking me, am I 100% sure that it is not 72? I said, I am 100% sure not 70. Actually, it was at 12, or not even, or it was around 10, or maybe less than 10. So this machine cannot be run more than 14 million volt. 14 million volt is theoretical value. Normally they run at 12, maximum 12.5. So they started increasing the value of the GBM 12 onwards. And you will be surprised, the operator could go up to 15 million volt. The reading on the machine was showing 15. This machine is not supposed to be giving more than 14, even theoretically. So then they realized that there is a problem in the particular reader, which tells you terminal voltage. Finally, that GVM was repaired and we could get the proper results. Incidentally, previous to our experiment, there was another group and they had a beam time of 5 days. And when they were going to quit the beam line and we are going to come, they were always grumbling. They did not get the data which they were expecting. So problem was persisting since that time. They were expecting some 120 MeV sulfur beam, but that is above the Coulomb barrier. But actually they were giving some 88, 90 MeV below the Coulomb barrier. So they did not get any results. So I had this in my mind also that why these previous people did not get any useful results. That is the out. So you need to have very keen observation that when you are doing some experiment, what you expect. So if you had done some simulation, you know what gamma lines you are expecting from the output. So that is how you can do corrections during the experiment. Otherwise, after 3 days, your beam time is gone. And then you see the gamma spectra is not, so your beam time is lost. The whole experiment may fail. That is what I mean. You need to have a keen observation of the parameters. Then the sample history also very important. The sample may undergo changes with time. Particularly, for example, if you are determining a metal ion concentration in a sample, you collect the sample from the field and take it to the laboratory. Suppose you are measuring at this field and then again you measure at the laboratory. Then because of the change in the moisture content, data may change. So always use dry weight wherever you are doing. Suppose the different laboratories are doing experiments. All the laboratories should follow the same protocol, SOP. So you take dry weight. Similarly, it's a good practice to preserve the samples if possible. Many times it's not possible to preserve. If you are doing destructive, you cannot preserve it. But if you are measuring, for example, the radiation effects on materials using a gamma ray, so gamma radiation effects, or you are doing some dosimetry, then it's possible to preserve the samples so that later on, the reviewer, when you send the paper for publication, the reviewer may ask to have more experiments or to repeat the experiment. At that time, you find if you have preserved the sample till your paper is published, it's always good to have preserving them so that you can repeat the experiment, whatever you are doing. The most important aspect of your data recording is if you are doing handling some instruments, then transparency in recording of data is very, very important. And so it should not only be appear to be transparent, but you should show that you are transparent. So for that, you should have a record of the raw data. Whatever data the instrument gives you in the form of an output, that is the raw data. So without smoothing, if you have the record of the data, then you are sure whatever data you are later on your results you are getting, based on that only you would conclude something. So the experiments reveal the truth. So if it is your instrument is faulty, you will get results accordingly, but rely on your data, whatever you are getting it, and sharing of the data and information describing the data collection method. So always share whatever data you have obtained and how you have obtained in your publications. Always show at least one set of raw data in your papers also. So the reviewer knows this is the quality of your data. So it is a good practice to show the raw data in your experimental work also. Don't manipulate the data to fit into known models. So you have many a times we have a hypothesis, and we always see that our data should follow that hypothesis. So you try to smoothen the data or try to fit into a particular mathematical form, though it may not be fitting it. So there is a tendency to manipulate, when you have something in your mind a priori. But I think that is not correct. Let the data speak for themselves. Like I give you an example, the output of a microcalorimeter, where you are titrating the one solution with another type solution, like a metal ligand. This is the data of a strontium solution. You are titrating with the crown ether. So when you add the crown ether complex ligand to the metal ion solution, as the drops are being added, you can see for each injection of the ligand, microliters, 10, 20 microliters, you get the peaks. And the quality of this, how many microwatts? 800 microwatts. So this is the titration graph. And if you show this data in your paper, the referee will know that what is the quality of this data. Similarly, if you are analyzing a sample for the total gas, suppose this is a deeply depleted uranium dioxide pellet, and you are finding out what are the gases occluded in the pellet, then this is the experiment of a quadrupole mass spectrometer. You are heating the pellet at high temperature and analyzing the gases by the quadrupole mass spectrometer. Like hydrogen is there, then you have the carbon monoxide, and even nitrogen and carbon monoxide, and you have the carbon dioxide. So they are the output of your quadrupole spectrometer. So this is the raw data. So once you show this data, the reviewer knows that this is correct. So there is no discussion about, and the intensities are also shown. So whatever data you will generate in tabular form, that is formed. So this kind of data has to be shown in the publication, and that is why such raw data should be preserved for future references. Then another important aspect is the quality assurance. So your data, the quality of your work will depend upon the quality of your data. And so you have to make sure, you have to ensure that the experimental data are correct. So how do you make sure that your data are correct? You have to convince the community whom you are addressing to calibrate the instruments periodically with the standards. Whatever instruments you are having, there will be some mechanism to calibrate that instrument. You will be having some standards. There could be faulty measuring systems like non-standard weights or scales. So keep note of them. So you should have those are properly calibrated. And to calibrate your instruments, there are standard reference materials. If it's the chemical analysis laboratory, you don't have reference standard materials, you have certified reference materials. So these kind of references materials should be there. And many a times you should participate in the inter-laboratory comparison exercise. If you are an analytical laboratory, participate and authenticate your methodology also. Not only the instruments, but the methodology that you follow should also be verified by participating in the inter-laboratory comparison exercise. Then the people who are operating the instruments, they should be properly trained. And whenever the new operator comes, then you should be training that person properly. Keep record of the change of operator. So sometimes, the systematic errors may creep in when you have a change of operator, and the new operator may not be as trained as previous one, or they may have their own biases. So these are the important aspects you have to keep note of. Then always read user's manual before using the instrument, as every instrument functions within certain range of observables or conditions of physical parameters like temperature, pressure, humidity, etc. So if you read the manual, you know in what range of these parameters this instrument functions. So you can keep many instruments, like for example, lasers. We have laser system, then the high humidity creates problem. You may have to have the dehumidifiers in the laboratory or particulates concentration. So all those things are important for proper functioning of your instruments. And then lastly, the error analysis. So whatever data you are generating, you must report the error bars on those numbers. So you should have a mechanism to know what kind of errors. So the errors could be random errors. Random errors could come because of many things. Whenever you are doing a measurement, there will be always, like your even the scale balance also has some least counts, your scale, the measurement, length measurements, weight measurements, anything you are volume measurement, they always have some least counts. So there will be always some errors. So random errors, you can minimize by repeated measurements. There are systematic errors creeped in. You can correct them by the process of calibration of your instruments. So, and then third is the bias. The bias is a general problem in research. Many a times, we have certain preset notion that this is how things should come about, and you are guided by that. So the bias refers to actions taken consciously or unconsciously by the experimenter that damage the validity of the experiment. So it introduces a systematic error in your data. One of the examples of how the bias can enter in your data is when the amount of data to be gathered is not fixed in advance, particularly when you are doing a survey or you are doing some sample collection. So you start analyzing. So the researcher goes ahead checking if the answer is in agreement with an expected value. So you may not be getting the data as you expect, and when it gets close enough, you stop taking data. So you are going on collecting the data like survey. You have to collect, let us say, some 1,000 people you have to survey. Then after 500 people you have interviewed or data collection, you found you got what you wanted. So you stop going further. And that is how you may introduce the bias. So to prevent that kind of a bias, fix the amount of data to be collected in advance. So that is why the research design becomes very important. How many data you will collect, how many samples you will collect, how many people you will interview, all that should be fixed in advance, and then analyze the data only after complete data collection. So this way you can minimize the bias in your data. Then there could be unknown uncertainties, as I mentioned, that certain things they can always come. You have not factored that those in your scheme. So I give you an example of the Robert Millikan's measurement of the charge of an electron, as way back in 1909. Millikan measured the charge of electron by this experiment of oil drops falling under gravity, and he applied an electric field that will move the drops upward. So there is a balance between the gravity and the applied electric field, and to make for a steady drop of the oil drop under this applied electric field. But then there is another factor here is the drag. It was necessary to know the precise amount of drag the air exerted on the droplets when they started moving. So when the droplets are falling down under the electric field, under the gravity, and then the electric field gradient to keep them up, there is a air drag. So the viscosity of air also plays an important role. And this required highly precise measurement of viscosity of air. And the viscosity of air depends upon the temperature. So you should do the experiment, measurement of viscosity of air at the same temperature at which you are doing the Prof experiment. So what happened actually, the viscosity of air were measured at one temperature, and Millikan's measurements were carried out at temperature few degrees different. And because of this difference in the temperature of the experiment and the temperature at which the viscosity of air was measured, the charge of electron came out to be 1% low, while Millikan's estimate said results should be accurate within 0.2%. So Millikan published the results with an accuracy or accuracy of 0.2%, but actually it was 1% low. It was only after some time that new experiments were proposed, then the actual value was found out. So you can see as precise experiments and Millikan's experiments also, they can have this kind of, because you do not, so when you are doing the experiment of viscosity of air, probably you may not have known at what temperature you measured this experiment. And so this can introduce the error of the order of, like you can see 1% error, and it was immediately reflected in the measurements. So this is what is important, that all the things have to be done in totality later on. Otherwise, you have to go back to see at what temperature you did the measurement of the experiment and the viscosity of air at different temperatures. So all these things are very important from the point of view of error analysis. So when you finally compile your results and conclude out of your results, so you predict and write your results and conclusions. They are the ultimate goals of your research. So it is like the nectar out of the Samudra Manthan that you say. So whatever you get, finally, they have to be really good quality data. The whole conclusion depends upon the data. So while interpreting the results, concrete results should dominate the imagination. Many a times, we have some results, but then we start speculating that, and then you start extrapolating also. So final outcome of our work may be different from what the data speak. So that is, we should not encourage. You conclude only to that extent the data reveals. Give all evidences relevant to the research problem and its solution. So whatever your data is giving, that only you use to draw any conclusion. Often, one may land up with unexpected results or findings contrary to the underlying theory. So you had something in your mind, but you are not getting what you are expecting. And don't ignore blindly, because you may be getting something new. It may reveal new signs. So don't underestimate your instruments or your thought process. You may be feeling that something may be wrong, so we should not, you try to see that your data follows what is already known. But it may happen that you may be getting something new findings, so don't ignore it. Do not rely on ambiguous evidence, which could increase the chance of errors. So sometimes there could be ambiguity. Like I give you an example here. You see, this is I have generated this data in an Excel sheet. So this was a straight line. And this data was here. So if this data is here, they will beautifully fit into an equation, a straight line. This is in fact a theoretical line. Now, what I did, this data is slightly pushed down. Now, if you look at it, you may be tempted to conclude that there are two straight paths. One is this, one is this. And many a times you start predicting that it's a step process. Suppose it is a melting of a compound and you are measuring the heat capacity or some enthalpy, and you may see there is a two-step process, one step and two step. But because of this only once, you have no point in between these 2 points. So if it is point slightly lowered, one straight line looks to be into two straight line. So this kind of misinformation may come if you don't. So that is why you can repeat this experiment again whenever you get this kind of data. Similarly here, so what I did actually, it was a Gaussian type of a graph. And you can see here, they are symmetric points. This point was here. But so it will look symmetrical. But the moment I brought this down, it looks more of a Maxwellian. So you are wondering whether this data is fitting into a Gaussian or a Maxwellian. And we may derive a new theory. So this can happen because by just one point. So always try to make sure that you have multiple points to help you in arriving at a conclusion. So whenever you have this kind of situation, because of this point, your whole outcome may change. You repeat this experiment and see whether it is really true. And if it is really true, then you have unearthed something new. So never yield to the temptation of fabrication of results and interpretation. Sometimes we tend to, because of this data, our data may not be complete. So, and you don't have time to repeat. So you try to push it up and say, okay, it's Gaussian, because you know in the literature it should follow Gaussian. But better is to repeat even if it takes more time. So the inferences should be based on logic and facts. So a good knowledge of literature and your confidence in your data helps in arriving at the firm conclusions of your work. So finally, some of the the wise words from literature. Landau was a Soviet physicist. His accomplishments include the independent co-discovery of density matrix method in quantum mechanics, along with John von Neumann, the quantum mechanical theory of diamagnetism, theory of superfluidity, etc. And about him, it is said that he never did for his students what he believed they should do themselves. Sometimes after many unsuccessful attempts to solve a problem, the student would ask Landau for his help. But Landau would reply, "This is your problem. Why should I do it for you?" So though he was the supervisor, he wanted that the students should solve the problem on his or her own. So never did he formulate problems for his students. This way, he trained his students to be independent and became future leaders of science. So many of his students became future leaders, but he allowed them to grow independently without his shadow. So that is what important. So you try to do all your experiments independently. Of course, that doesn't mean that you don't go to your supervisor. Definitely you have to seek his advice, but try to do the experiments as independently as possible. Now, if you see in the literature, what are the best experiments in science? I found this is categorized as one of the best experiments in science, and that is the discovery of polonium and radium in it is not 1998, it is 1898. So 1898, Madame Curie and Pierre Curie, they in fact discovered two elements, polonium and radium. In 1896, Henry Becquerel discovered radioactivity in the compound pitch blende. And this pitch blende is the ore of uranium. And then in his laboratory, Henry Becquerel's laboratory, Pierre Curie and Madame Curie wanted to investigate this phenomenon of radioactivity. What they found that all compounds and minerals that contain uranium were active, and the pitch blende, the ore of uranium, a massive variety of uraninite from a particular mine in Austria, as well as chalcolite, a natural uranium phosphate, they were much more active than metallic uranium itself. So from the uranium half-life, you can find out the specific activity. That means 1 gram of uranium should give this much activity. But they found that this pitch blend was having much more specific activity than uranium. And so Madam Curie writes in her memoirs, in her publications, this fact is quite remarkable and suggests that these minerals, which blend and so on, may contain an element much more active than uranium. You see, why I wanted to show is that the statements that you make about your work should be straight away coming from your observation. So you have to be very cautious. So they say that these minerals may contain an element. They are not very sure, much more, which is much more active than uranium. Then subsequently, they analyze this pitch blend, try to precipitate that other activity from uranium, and again they conclude like this. In fact, December 28, 1898, they discovered the element radium. And what are the evidences? They have written categorically. This active element, they have not named it so far, active element precipitated with barium. So when you do barium sulfate precipitation, this activity precipitated with barium. Second evidence, the radioactive element could be separated from barium by fractional crystallization. So they have done this experiment. And third is that the spectral lines of radioactive element would not be assigned to any known element. So this is a new element. So this is the kind of language, statement they used to tell that they have discovered a new element. They have not, they told they have discovered new element. They told that this element precipitated with barium, it can be separated from barium, and the spectral lines of this element cannot be assigned to any other element. And for this discovery, Nobel Prize was given to this group of 3 people, Henry Becquerel, Pierre Curie, and Marie Curie. And it is not the end of the story. One of the best, the first ever radiochemical separations, were done by Madame Curie on this pitch blend. And they published this work on a new radioactive substance contained in pitch blend, that is polonium. Pierre Curie and Madame Curie. And here they write, we believe that this is about polonium. Again, in the 1898 itself, this is not 1998, 1898. We believe that the substance we recovered from pitch blend contains a heretofore unknown element similar to bismuth in its analytical properties. If the existence of this new metal is confirmed, we propose that it be named polonium in honor of the native land of one of us, that is Madame Curie. So this is the way they announced the discovery of the new element, which they proposed to name as polonium. And you see here the enormity of the experiment. In 1910, see, when you want to discover a new element, you have to confirm it by the spectral lines. And to see the spectral lines of an element, you should have it in milligram quantity. Madame Curie in 1910 separated 0.1 milligram of polonium from several tons of pitch blend to confirm its spectral lines, which was a prerequisite to discovery of a new element. So that actually gave that explains why these were the best experiments, first radiochemical separation experiments, and one of the best experiments in the history of science, where from several tons of pitch blend ore, she could separate 0.1 milligram of polonium to tell that this is a new element and that she proposed to name as polonium. Another very good experiment, very precise experiment, and it also tells many important aspects when we do the interpretation of our results. Ernest Rutherford did this experiment of scattering of alpha particles by the gold metal foils. Now, these alpha particles are now obtained from the radium source, and you collimate the beam of alpha, fall on gold foil, and these gold foils, the alpha, when they pass through this gold foil, they will produce scintillation at the zinc sulfide screens, and which are placed at different angles, 0 degree, 45 degree, and some of them at backward angle. Now, when he was studying the scattering of these alpha particles by the gold foil, he found that 1 in about 8,000 alphas was scattered in backward direction. You see, this, I wanted to highlight this aspect many a times, if you get one scintillation in this and 8,000 scintillations in this, you may say this is noise. So you tend to ignore this one count here. There could be some fluctuation and all that. But he was so sure of his experiment that this one count, in fact, led to his discovery of nucleus. Because first of all, he was surprised. He in fact tells that it was quite the most incredible event. It was almost as surprising as if a gunner fired a shell at a piece of tissue and the shell bounced right back. So he expected that these alpha particles, bullets, 5 million electron volt energy particles, should just pass through this gold foil and hit here. So that surprising backscattering of this alpha was a surprising result. But then he believed his data and then gave to the conclusion that the mass of the atom is confined in a very small volume at the center of the atom. That is what is called as the nucleus. So it is an incredible event, which probably we may not have expected, but when it got, he gave the interpretation, and that is Rutherford's backscattering became a house. Now in the physics community, nuclear physics, Rutherford backscattering is utilized even in material science by ion beam analysis and so on. So that is the kind of evidence you have to bring out a new theory or new model. Now I will give you an example of a yes quadrant. We mentioned in the first lecture or maybe second lecture that you may have this yes-no quadrant of Niels-Bohr, where you do fundamental research, but it may not have any consideration of use. Or you may do work in a distance quadrant where you may have a lot of application, but it is not based on any fundamental knowledge. And then the Pasteur's quadrant is yes quadrant, where you use the basic knowledge and then try to solve some problems of the science or even for the technology and so on. So this is an example of a yes quadrant where you, based on the basic theory, you try to solve the fundamental problems in science. So the problem relates to the aging management of coolant channels in PHWRs. The pressurized heavy water reactors of Nuclear Power Corporation of India Limited, they the coolant channels through which the coolant flows, they undergo aging. So that aging happens because of the hydrogen and deuterium. Now the PHWR have only D2O, heavy water. There is no hydrogen. So this deuterium, because of the deuterium may get attack the coolant channel. The coolant channel made of zirconium niobium alloy, and gradually this deuterium may diffuse inside and form deuteride, or like hydride, and the hydrides have a damaging property that leads to stress corrosion cracking. So before the stress corrosion cracking takes place, they are removed. So, and that happens after maybe a few years. So before that fuel, the coolant channels fail, the engineers try to do aging management. In that aging management, what they do, they scoop out a portion of the coolant channel, bring it to the laboratory to measure the deuterium content. This zircon niobium at room temperature, it can contain 28 ppm. If it contains more than 28 ppm of deuterium at room temperature, it will form deuteride. So it's a different phase of zirconium that will form blisters. So before it reaches, or at 250 degree, accordingly, every 50 degree, it goes up, doubles the deuterium content. So they need to measure the deuterium content periodically so that we don't exceed that concentration, which will lead to blister formation. And that is done. These sliver samples, they are scooped out from very few 100-micron samples are brought to the laboratory, and by hot vacuum extraction, quadrupole mass spectrometry, that measured the deuterium content in these samples. But along with this deuterium, when the samples came to our laboratory, these samples showed high concentration of hydrogen also, though PHWRs do not have any hydrogen. So the engineer who was bringing the samples to us, they were asking, you are not reporting this hydrogen. Why? Whether there is no hydrogen. So I asked my colleague, what is show with the data? He told that the hydrogen content is quite high, but it should not come there. So that was the problem. And so we discussed this. So where from the hydrogen is coming? So the problem was, what is the origin of hydrogen in coolant channels of this PHWR? Whether it is present in coolant channel, or it is happening during the slivering, or at what point there is a pickup of hydrogen. So to solve this problem, we prepared a plan for understanding the diffusion of hydrogen and deuterium in coolant channels that is made up of zirconium 2.5% niobium. So this is how. So we made a research plan. The research plan was like this. Okay, I'll discuss the research plan. So this is the experiment instrument. This instrument, in fact, is designed indigenously in our laboratory. Indigenous effort based on hot vacuum extraction. You heat the sample at very high temperature, and the evolved gases are analyzed by quadrupole mass spectrometry. These are the hydride blisters, that can happen if the hydrogen or deuterium content goes above the terminal solid solubility, and finally it can lead to failure of the coolant channels. So this is the instrument, and this is where our colleague is doing the measurements. So determination of hydrogen and deuterium content in sliver samples of coolant channels of all PHWRs is done using this instrument. And this is recognized and ideal for aging management of coolant channels. So you can also do by differential scanning calorimetry, but that will give the total of the hydrogen and deuterium. And as a part of this exercise, hundreds of samples from all the PHWRs are analyzed for their hydrogen deuterium content. So how to resolve where from this hydrogen is coming? So for this, we made the experimental plan to study hydrogen deuterium diffusion in zirconium-based alloys. So what you have to do, you have to charge the hydrogen deuterium electrolytically in these alloy samples. So you take D2SO4 and in normal water. So you can play with the ratio of hydrogen to deuterium. And after sufficiently annealing and electrolyzing, the hydrogen and deuterium will diffuse into the alloys. Then you can anneal the samples at different temperature to diffuse them into the bulk of the sample, then cut them into thin slices of 2 mm each, and analyze those slices by hot vacuum extraction, quadrupole mass spectrometry. So this is the data. You can see here. So you charge them at one end, maybe 1 or 2 millimeters is charged, and then you see the diffusion of hydrogen deuterium as a function of depth up to 20 millimeter. This is the concentration of deuterium in ppm. So this is the typical concentration profile of deuterium. Similar thing you got for the hydrogen. And then you can also see the microscope in the electron microscope. The needle shaped are the hydrides. And as a function of depth, the concentrations are going down. So you can then analyze the temperature dependence of this diffusion coefficient to find out the activation energy of diffusion and the frequency factor for deuterium and hydrogen. But they found that the activation energy was same. The diffusion, the Arrhenius factor has to be different because of the mass difference. So what they found that the diffusion of hydrogen is higher than deuterium, but it is not high enough to explain there's such a high concentration of the hydrogen in the saliva samples. It was concluded that that hydrogen is picked up by the alloy samples when they are being handled from the field to the laboratory. So because zirconium is a highly pyrophoric material, it can pick up moisture very quickly during handling. So this is the outcome of that study. So it was assumed that there is no problem in the data. So the hydrogen data can be ignored. And one more example of last example of this one is the online gamma spectrometric measurements at power reactors, primary heat transport, and moderator pipelines. In fact, that was in 2005 that I got a phone call from our friends in Narora in the PHWR. What they found when they shut down the reactor in the primary heat transport line, where there is a they go for maintenance during the shutdown, there was a high radiation field. Now, the radiation field should not have gone up. So they were very much surprised why this radiation field should go up and how people will go and do maintenance work. So because people will be receiving the high radiation dose. So the question before us was, what is the source of the high radiation in the primary heat transport lines after the shutdown? This is the question that was posed to us. And now you see, when we have to plan the experiment, I was told that the radiation field in that area is 1.2 rad, very, very high. You cannot work in such an area. So you require a detector system at such a high dose, and it's a humid atmosphere, and there will be a lot of pipelines. So you need a suitable detector to do and find out the radioisotope, radio line, gamma lines, to tell what radioisotopes are involved in this one. So sodium iodide thallium is a normal detector we use for room temperature, but it has got a poor energy resolution. So you cannot be used to identify the gamma lines and hence the radionuclides. Other detector is high purity germanium detector, which has got a very good resolution, gamma resolution, but it is a bulky. It has a liquid nitrogen cryostate, so it cannot be taken for the field work. So it is cannot used in the field. So we have to look for a detector which has a better energy resolution than sodium iodide thallium and can be operated at room temperature. So that was the issue. So that is where now it's a knowledge of gamma spectrometry. If you are working in a basic research area, and if you have the wherewithal to have access to such instruments, so we had a detector at that time called cadmium zinc telluride. This is the detector coupled to the preamplifier and the FET based system. And there is a 20 feet long cable goes to the palm top PC. And this has got a 0.5 cc volume, very small. It is ideal for working in a high radiation field. So what I did, I put it in a lead pot so that we have a collimation. And at the end of the lead pot made a 10 mm hole. So the detector is shielded from the radiation background and gamma ray will come only from the front through a 10 millimeter hole. This is a large band gap semiconductor detector, 1.6 electron volt. So we can operate at room temperature. We add this zinc to increase the resistivity of the detector, and it is available in small size, 0.5 to 1.5 cc. And resolution is, instead of for cobalt, for sodium iodide thallium, it is 60 keV. For zinc, cadmium zinc telluride is 12 keV. So it is quite good to resolve the individual gamma lines. So we took this detector to Narora and then did the gamma spectrometric measurement. So we don't have to be near the 1.2 R dose. We can be away 12 feet, 20 feet away and keep the detector in the beam line, the pipeline. So this is the gamma spectrum. So this is the raw data. Always show the raw data. And you can see here, this is antimony 122, antimony 124, 603 and 1696, cesium 137, niobium 95, cobalt 60, barium 140, and antimony 124 again. So a typical gamma spectrum, we could unambiguously prove that this high radiation field in this is coming due to 124 antimony, which has got a half-life of 60 days. And then we repeated these experiments. Other station people also called us, Rajasthan, Kakrapar, Tarapur, everywhere. So it was later on found out this that the CANDU type of reactors have this problem. So the conclusion of the study: what is the source of high radiation field in the primary heat transport lines post shutdown? Is it because of 124 antimony? How is it formed? So it was later on found out that the primary coolant pump of this uh, reactors contain the carbon brushes contain antimony impurity, and this antimony impurity by neutron activation becomes 124 antimony, and this is into the goes to the core of the reactor by wear and tear, and then during the shutdown, because of oxygen ingress, it goes into the pipeline and deposits in the magnetite layer of the primary heat transport system. So what is the solution? Solution was dilute chemical decontamination for removal of antimony from magnetite layer in the primary heat transport system. So that is how the solution problem could be solved thanks to the basic understanding of the whole phenomena and the availability of good detector systems to probe the radioisotopes. So these are some of the examples I thought I can share with you my own experience. Okay, so finally, some of the wise words from our uh, forefathers. So that they say, don't be afraid of not knowing. Richard Feynman says, very, very important prophetic words. He used to say, I had no fear of doubt and uncertainty. I don't feel frightened by not knowing things, by being lost in a mysterious universe without any purpose. It doesn't frighten me. So doubt is motivation. It leads to discovery and pleasure of finding things out. So if you don't know anything, we don't have to be shy of it or don't have to be afraid that we don't know, because we cannot know everything. And then the 16th century academician Francis Bacon said, if a scientist will begin with certainties, she shall end in doubts. But if he or she will be content to begin with doubts, he or she will end in certainty. So I think I mentioned this in the beginning itself, that don't doubt everything and don't believe everything, but if you doubt, then be ready to accept the reasons behind that. So you don't have to be absolutely doubting everything and don't believe absolutely everything. So lastly, some of the important suggestions for you, points to note. A researcher must be clear in his or her thoughts, should know what to find out. So clarity of thoughts is very important. Scientific research is like sports. So take it like a sports wherein the failures and successes are part of the research work and we learn from your failures. So don't be afraid of failures. If you fail in one experiment, you learn from that experiment much more. So perseverance, tolerance, and self-control are important attributes of a good researcher. Enjoy doing research and approach it as a mode of getting happiness. In fact, Carl Friedrich Gauss, German mathematician and physicist, told a very, very nice thing. It is not the knowledge, but the act of learning. It is not the possession, but the act of getting there, which grants the greatest enjoyment. So you don't be always obsessed with getting some positive results. When you are doing PhD, you are undergoing a training on how to do research. So the very journey itself you should be enjoying. So you have been given an opportunity to develop new knowledge. Even if you fail in an experiment, you will get a new knowledge that this is not the way to go somewhere. There is some other route. So that is what is the lessons we learn from this kind of experiments which do not succeed, but then later on, definitely you will find success in the improved experiments. So thank you very much for your attention. And if you have any questions, you can write in your chat box. Let me see the chat box. Okay. What are sliver samples? So these sliver samples are, so there is when the reactor in fact is running, they introduce a chisel type of thing, a chisel which will scoop out, like, you scoop out ice cream from the ice cream box. You go to ice cream shop. So the way he scoops out, this chisel will scoop out a 100 micron thick layer piece of this coolant channel, and that, so the zirconium alloy, it will chisel out, and that is brought in the proper shielding to the laboratory for analysis. That is what is called the sliver sample. Okay, so I don't have to go up. We will go down. If you have any questions, you can ask me. You can, if you are writing in the YouTube, my colleague will transport them to me in this, and I'll be able to read them, but it may take a minute or so. Yes. So this is the question: when there is no change in the chemical shift value of probe nuclei, will that be called bias? Okay. Sir, if we in a titration using NMR, we stop taking data where there is no change in the chemical shift value of the probe nuclei, will that be called bias? So the chemical shift in the NMR essentially are telling you the chemical environment in which the proton is sitting. So if you record the NMR spectrum for the full range of the radio frequency, then if there is a change in, if there is no change in chemical shift, that, see, once you have raw data with you and you don't find any chemical shift, that means the chemical environment, all of them are in the same chemical environment. So I don't think it is called a bias. We stop taking data when there is no change. So here you have to scan the full frequency range, because your different protons may appear in different frequency domain or the magnetic field domain. So you have a range of magnetic field or frequency. You have to scan the full area. You don't have to stop. But I don't think this will show any bias. Your NMR spectrum and will anyway go to the full range of frequency or field. So their chances of introducing bias are not there. It is when you are like, when you are collecting some data and you found something useful which meets your expectation, you stop collecting further data. But in NMR, you have to have the full range. Your instrument will give you the full range of frequencies. So that may not be really, this is not a proper analogy that it will introduce any bias. Okay, sometimes we attend using YouTube if WebEx is not working. So will attendance be considered if we watch from YouTube rather than WebEx? If you are writing your name and affiliation in YouTube, that is also noted down. So you don't worry about it. It is being noted down. Like, some of you are writing the questions in chat box in YouTube, and I'm able to get them because my colleague is sending them to me. I'm able to read them. So you don't worry about your attendance, whether you are attending from WebEx or YouTube. Yeah. Can failures also be published? Yes. Negative results can be published. I will not say failures, negative results. If you have a proper objective of your experiment, and so like, your hypothesis, you have an hypothesis and you have you have some expectations, and you don't, so suppose you have two mutually exclusive options. So option A and option B, you expected A, you don't get A, so option B is true. Option B true also can be published. So in fact, I can tell you that one of my students has submitted his thesis on radiation effects on glasses, and he did not get any effects of radiation on those glasses, but the papers are published. So these glasses are stable to radiation up to this much dose of gamma ray. That is the outcome. You cannot say they are stable to radiation, but they are stable up to that much dose. We could not go to higher doses. So up to that dose, they are stable. That's the way. Okay. Okay, there is a question. Objective of research proposal. This question is only written as objective of research proposal. I am not very clear what Pragati wants. So the research proposal, every research proposal has some objective. You have to define whether it is hypothesis based or you are measuring a value or you are doing some observation. You will always have some objective, which you have to be very clear. Rutherford put 360-degree zinc sulfide from first day of experiment. Mean how to you know alpha particles scattered from gold foils. So this is the first experiment to understand the structure, internal structure of the gold foil. So gold foil you see, as you see, is a yellow color. So you want to know what is the smallest entity which you can probe. So like X-ray will tell you the atomic arrangements in the crystal. But you want to know further inside the atom, what is that? How the material is arranged in a metal foil. So he used a gold alpha particle as a bullet to understand, and he put it is not 360-degree. When you say backward scattering, it is not necessarily 360-degree. Even at 120-degree, 150-degree, it is back scattering. So more than 90 degrees back scattering. So he put the detectors at forward angle and backward angle, and he found very few of them are also coming in backward angle, which was not expected from the energetics. But then once he found that some alpha are backscattered, he gave the theory of the nucleus. Any other questions? Okay. So if there are no more questions, thank you very much. And then we will discuss now the statistics part of this course in the next lecture on Monday, 4 o'clock. Okay. Thank you. Bye-bye. All the best.